Hello, my dear student. Welcome to EPG Pathshala. I am Anshul Srivastava from Department of Physics, Institute of Science, Banaras Hindu University. Today, we are going to talk on module titled Growth of Semiconductor and Oxide Nanowires under the paper Nanoscience and Technology 2. After completing this module, my dear student, you are able to learn about one-dimensional nanowire or quantum well on the basis of quantum confinement. You will learn the synthesis techniques for growth of semiconductor and oxide nanowires. You will also learn the template-based growth of nanowire and pulse laser deposition and thermal evaporation techniques in detail to grow the nanowires. One-dimensional structure have been called in different ways, maybe nanowire, nanorod, fibers, fibrils, whisker, etc. The common characteristic of these structures is that all they have a nanometer size in one of the dimension, which produces quantum confinement in the material and changes its properties. Nanowires are structures with at least one of their dimension in the 1 to 100 nanometer range. Typically, they are several micron in length with diameter under 100 nanometer. Nanoscale materials exhibit a very high surface to volume ratio. A 30 nanometer iron particle has about 5% of atom on the surface, and a 10 nanometer particle have a 20% of the atoms on the surface. In contrast, a 3 nanometer particle have 50% of atom on the surface. This makes the surface or interface phenomena to dominate over bulk effects and strongly influence adsorption, solubility, reactivity, catalysis properties, etc., where surface effects are important. In addition, as mentioned earlier, the size dependent properties make nanoscale material attractive in various applications. In any application, the material selection is made based on one or more desirable properties of material over its competition. Fundamentals to this revolution is the development of nanostructured material and inorganic nanowires form a class of nanomaterial that is expected to play a prominent role. Attempts have been made in recent years to grow the above materials in the form of one-dimensional nanowires. The future of inorganic nanowires. The nanowires are mostly single crystal with well-defined surface structural property. When their dimension, especially the diameter, is less than the Bohr radius, the resulting quantum confinement is of great interest in studying the excitonic behavior of low-dimensional solids for its effects on electron transport, band structure, and optical properties. The electronics, their one-dimensionality, offers the lowest dimensional transport channel for best field effect transistor scalability. The interesting properties of various nanowires make them better candidates for a wide range of application. Dear student, you can see these things in table 1 of the unit content section. However, I want to read few of them for your ready reference. If I talk about the silicon material, which is well known, their application in electronics, biosensor and solar cell are well known. Similarly, the germanium nanowires has application in electronics and IR detectors. Tin oxides nanowires are very good for chemical sensing. Indium oxide also used in chemical sensing as well as biosensing. Indium tin oxide is used for transparent conductive films in display electrodes, solar cell, LED, etc. Zinc oxide is very known material, especially nanowires, has been used for UV lasers, photodetectors, UV LED, field emission devices, etc. And gold nanoparticles or silver nanowires is for biosensors. It is also possible to conceive of system wherein various nanowires can be employed for different functions as shown in the figure. Silicon or germanium nanowires for precursors, phase change nanowires for memory, oxide nanowires for sensing, thermoelectric nanowires for power generation, third, fifth periodic table nanowires for optoelectronics component, and some examples to build integrated system. I want to discuss the growth techniques of nanowires. Growth processes must be able to preferentially support growth in one dimension. The key requirement for growing nanowires are that there must be a reversible pathway or condition near equilibrium between a fluid phase such as solution, melt or vapor and a solid phase, and also the atoms in solid phase should have high surface or bulk mobility. The nanowire have been synthesized using variety of techniques. The nanowire synthesis methods can be divided into two broad categories. The first one is liquid or solution based technique, and the second one is vapor phase technique, which is shown in flowchart. The vapor phase techniques include methods such as vapor phase deposition or chemical vapor deposition using catalyst metals, chemical vapor transport, reactive vapor transport, laser ablation, carbothermal reduction, chemical beam epitaxy, thermal evaporation, and thermal decomposition. Plasma and current induced method is also possible. Liquid or solution based techniques include approaches such as sol-gel synthesis, hydrothermal processes, and electrode deposition. Many liquid phase techniques utilize template for producing one-dimensional material. Through techniques without the use of templates are being developed rapidly. In this module, we will learn about growth apparatus for these techniques along with source material, growth conditions, substrate preparation, catalyst preparation, and post-growth processing. I want to discuss liquid phase technique, which is template-based liquid phase technique. There have been a number of approaches for nanowire synthesis using liquid phase. This can be divided broadly into two categories. The first one is template-based and template-free approach. First, I will discuss template-based method. Schematic showing nanowire electrode deposition techniques based on positive and negative templates have been shown in figure A and B respectively. Template provides one-dimensional channel for guiding the growth or deposition of material in one dimension. There are three primary types of template: the positive template, the negative template, and surface step template. Among these, the negative template method is most commonly used among the three. There are also three main deposition methods using these templates. The first one is electrode deposition, second is sol-gel, and the third one is chemical vapor deposition. Other less popular techniques involving templates include chemical precipitation or polymerization reaction and electroless deposition. Now, let us understand the template preparation, first positive template approach in detail. In a positive template approach, the one-dimensional nanostructures such as carbon nanotubes, DNA, and polymers are used as a templates to deposit the materials for nanowire production. This is schematically shown in figure A. CNT provide an ideal confined platform for chemical reaction. In principle, it is possible to obtain nanowires of any material by simply depositing it using sputter coating or electrode deposition or thermal treatment onto CNT. However, this is not possible for all types of material because of weak metal-carbon interaction. Physical vapor deposition results in discontinuous structure on the CNT after deposition. However, titanium has strong interactions with CNT and hence it can be used as a buffer layer to increase the adhesion for obtaining nanowires of other metals such as gold, palladium, iron, aluminum, or lead, etc. Again, I will discuss the liquid phase technique, which is template based. Another template approach is the negative template approach. In a negative template approach, a prefabricated hollow cylindrical structure is used to deposit the material of interest inside the hollow pores in the one-dimensional form. This is shown schematically in figure B. Potential templates include nuclear track etched membranes, anodic or anodized alumina membranes, die-block copolymers, nanopores array in glass, mesoporous silica, and other porous or hollow structures. Anodized aluminum membrane is another commonly used negative template, which is known as AAM, produced by well-known anodization process. Anodization involves placing an aluminum foil in a chemical acid bath electrolytic solution under a direct current, which develops a self-assembled pore structure as shown in figure. The aluminum sheet becomes the anode, whereas acidic solution becomes the cathode during anodization at oxide film form at anode. This involves a reaction 2Al solid plus 3H2O liquid is equal to Al2O3 solid plus 6H plus 6E minus. While hydrogen evolves at cathode platinum, 6H plus 6E is 3H2, which is gas. The electrode potential at the anode is given by E is equal to minus 1.55 minus 0.059 pH. Thus, the reaction at the anode is determined by the pH, which in turn depends on the electrolyte and the temperature. As the anodization processes, the growing oxide layers is also dissolved by the acid, leading to formation of pores shown in figure 4b. Thus, the acid action is balanced by oxidation rate to form microscopic pores. 10 to 150 nanometer in diameter and length up to several micron can be achieved. The bottom of each pores also consists of thin 10 to 100 nanometer thick oxide barrier layer over the metallic aluminum surface. Also, pores are formed only when aluminum anodization is done under acidic condition, pH less than 5, using acids such as H2SO4, H2C2O4 or H3PO4. There are various methods for deposition of material inside, outside, or on the template for creating material of your choice in one-dimensional form. These methods include electrode deposition, sol gel technique, chemical vapor deposition technique, chemical precipitation technique, or polymerization reaction technique, nevertheless electroless deposition technique, etc. Each deposition method works better with a type of template for a certain type of material system. Let us talk about electrochemical method. In electrochemical template synthesis approach, the working electrode, which is cathode, where deposition is done, consists of prefabricated template or an electroactive support for growing nanowires, and the electrode deposition is carried out in a standard 3 electrode electrochemical cell with a counter electrode and reference electrode. The cathode or the working anode is connected to the negative terminal of an external direct current power supply and anode to the positive terminal. Both these electrodes are immersed in the electrolyte that contains the metal ions to be deposited on the cathode during the experiments. The deposition starts from the base of the electrode, resulting in well-defined structure through the templates as a nanowire. Now, let us discuss the salt gel synthesis technique. The salt gel template-based nanowire synthesis method rely on capillary action or electrophoresis of the pores in the template to fill the pores with salt particles. In a simple process, as shown in figure, the template is dipped directly into a relevant salt containing the precursor material and heated for some time. Salts are the colloidal suspension of solid particles in a liquid dispersion. Salts are formed when the starting metal salt or precursor is processed through a series of reactions, hydrolysis, to form a colloidal suspension, that is salt. Gel are the integrated network, semi-solid and liquid, comprising the salt along with the other liquid phase solution ingredient formed by condensation reaction. Salt gel process involves the transition of a system from a liquid salt to solid wet gel phase. The method is based on the hydrolysis and condensation reaction of precursors. Commonly used template is porous AAM. The pores of template are filled slowly by compact stacking of the salt nanoparticles. If the deposition time is short, the particle deposit first on the wall, leaving wires in the center, eventually making nanotubes showing in figure A. Whereas longer deposition time results in nanowire, which is shown in figure B. The final product is obtained after a thermal treatment to removal of the gel. Alternatively, salt gel electrophoresis can also be used where the template pores are filled by movement of salts under an applied electric field. Vapor phase techniques for nanowire growth. Vapor phase synthesis is the primary method for synthesizing nanowires in a number of material systems. Several vapor phase methods has been developed to an advanced stage compared to liquid phase method. This method can be broadly divided into two categories: substrate based and substrate free direct method. Schematic of two general methods used for vapor phase synthesis of nanowire is shown in figure A and B, where figure A is substrate based method using a horizontal chemical vapor deposition reactor, and figure B is the direct gas phase nanowire synthesis method. Let us first discuss the substrate based method. Typically, in any this method, the substrate is placed downstream to the source. The reactor operating under vacuum is heated and the source vapor reacts to produce the responsible growth species. which then deposit onto the catalyst supported by the substrate. The substrate has been found to be essential for nanowire synthesis in the vapor phase method for the following reasons. Reason number 1. The substrate supports the catalyst cluster and allows control of cluster temperature. Second, induced preferential precipitation at substrate catalyst cluster interface. So the use of a substrate is essential for maintaining one-dimensional growth in vapor phase method involving catalyst clusters. Now, the second one is substrate-free method. Let us discuss this. In this method, a vertical reactor is used where a microwave plasma discharge, which is the reaction zone, is generated by passing reactive gases in confined inside a vertical quartz tube. The source material is allowed to fall under gravity and it is collected in a cup. The key advantage of this approach over a substrate-based method is bulk production. Since the use of substrate limits the amount of nanowire which can be produced, this method can theoretically yield bulk quantities of nanowire. Let us discuss the thermal evaporation technique. A typical reactor setup used for thermal evaporation contains a horizontal tube furnace with provision for gas flow and pressure gauge with or without control, which is schematically shown in the figure. The furnace may have a single, 2 or 3 heating zones. More than one zone allow a hotter source generation zone with relatively cooler growth zone. The experiment are typically carried out at low pressure, achieved using by mechanical pump, so that the reactions over catalyst can be selective. Low pressure operation can also help to reduce oxygen contamination whenever it is critical. The desired source material to be heated is placed in an alumina crucible. The crucible material should have high melting point, good chemical stability, and hardness so that it can withstand high temperature and chemical corrosion. The tube furnace heated up the source through conduction, gas convection, and radiation. Alternatively, the source material can also be heated by resistive heating of the crucible. It is important to bake and purge the reactor before each experiment to remove absorbed gases from reactor walls and reduce contamination and oxygen partial pressure. The source gases diluted in an inert gas such as argon are used. The purged source vapors produced from thermal evaporation, for example zinc oxide vapor, or source vapor mixed with other feed gases, for example in vapor mixture with ammonia and indium nitride growth, reacts on the substrate kept at a distance from the source board. Note that the source material do not to be a very high temperature close to their melting, decomposition or sublimation point to produce enough vapors. In downstream, there can be a provision for cold finger or a substrate where temperature is lower. This is the region dual zone furnaces are preferred. Due to low pressure uses, the nanowire growth occurs over a prolonged deposition time, maybe few hours, if long nanowires are desired. Typically, the nanowires produced products are collected near the downstream end of the tube furnace, where I am going to discuss the pulse laser deposition technique for growing nanowire. Pulse laser deposition or laser ablation is another low pressure, high energetic, non-equilibrium, rapid condensation process for producing nanowire. The schematic of a typical laser ablation setup has been shown in the figure. The setup is almost similar to that for thermal evaporation, except there is a port for introducing the laser beam and a target containing the source in the middle of the quartz tube. The laser, when it is hit the target, generates a plume containing vapor fragments of the target. The target is made by pressing the source materials and the catalyst metal together into solid cylindrical pellet. The chamber temperature is maintained using the tube furnace at a level needed to sustain the catalyst molten alloy, or for a nanowire growth, typically between 800 degrees Celsius to 1200 degrees Celsius. The variables in this method include laser power, target composition, gas phase composition, temperature, pressure, residence time of vapor phase species, and cold finger conditions. Laser ablation in general is not a scalable process and therefore is suited for laboratory investigation. A large range of semiconductor compounds such as binary third, fifth nanowires, which is gallium arsenide, gallium phosphide, indium phosphide, and binary, which is second and sixth nanowire, zinc sulfide, zinc selenide, cadmium selenide, and ternary third, fifth nanowire, which is gallium arsenide phosphide, indium arsenide phosphide alloys, or alloys like silicon germanium, has been synthesized by them. Similarly, metal oxide nanowires of iron, zinc, tin, gallium, etc. Metal nanowires like silicon germanium have been obtained. Silicon nanowire have been produced using silicon iron targets with rhenium, yttrium, aluminum garnet (NdYAG) laser, irradiated at 2 watt average power, 10 Hz pulse rate, and wavelength of 532 nanometer in 50 SCM of argon flow, standard cubic meter. The SI 0.9 and Fe 0.1 target was ablated to create the source vapor, and the nanowire were deposited on the cold finger while the tube furnace was maintained at 1200 degrees Celsius. The resulting silicon nanowires were 10 nanometer thick and several micron long and consist of Fe-rich cluster at their tip. So student, let us now summarize what we have learned in this module. It is possible to design a system wherein various nanowires can be employed for different functions. There are several synthesis techniques available to grow nanowires. In liquid phase growth, two types of template, the positive and negative approach could be used. Pulse laser deposition technique could be used for growth of nanowires too. Thermal vapor deposition technique is also suitable for the bulk growth of nanowire. Thank you.